Welcome to Physics 4A Problem Solving Companion 8. In this video, we will look at problems that require using energy and momentum conservations and related concepts. This companion video is paired with Physics 4A Lecture 13 Impulse and Momentum and Physics 4A Lecture 14 Analyzing Collisions. We work out questions from a wide range, from one that requires mixed problem-solving strategies to ones that will relate force, impulse, and momentum to each other, and to ones that show momentum conservation in a variety of situations. We will end this set with a few questions that use conservation of energy and momentum together. In particular, regarding elastic collisions, we will illustrate three different solution approaches, each with its own strengths and drawbacks. Following are the sections in this video. All the chapter and problem number references are for OpenStax University Physics, Volume 1. First, our mixed strategy question. Energy for speed, force for tension. Solving Chapter 8, Problem 44. Then, relating force to impulse. Impulse as area under f of t curve. Solving Chapter 9, Problem 32. And getting into momentum now. Force as momentum flow. Solving Chapter 9, Problem 29. Continuing with rocket momentum and approximations. Solving Chapter 9, Problem 78. Momentum, impulse, force, and energy loss. Solving Chapter 9, Problem 37. Internal work, conserved momentum, with the use of SageMath. Solving Chapter 9, Problem 38. Momentum by components. Solving Chapter 9, Problem 62. Energy plus horizontal momentum. Solving Chapter 9, Problem 117. Beginning the series on elastic collisions. Kinetic energy plus momentum by hand. Solving Chapter 9, Problem 49. Kinetic energy plus momentum with SageMath. Solving Chapter 9, Problem 98. And finally, relative velocity, the linear shortcut. Solving Chapter 9, Problem 49 again. This set is much longer than usual in order to cover all the different approaches to mechanics problem solving we can handle now. It is my hope that you will develop your own problem solving skills, mastering these approaches and learning to solve entirely new problems on your own. All right, let me start by reading the question. It says, a small ball of some mass is tied to some string of some length and is set rotating with negligible friction in a vertical circle. Okay, at the top of the circle, it is moving at speed v. Answer the questions below in terms of m, l, v. Okay. So I like to draw a picture of what this looks like so that I have a concrete physical picture in mind. This is especially important thing to do as you approach any question using conservation of energy and momentum problem solving strategy, because this is the one weakness of conservation law strategy, in that it doesn't go through every single detail. That's a strength, but it's also weakness, because so you have to fill in that gap and make sure all the picture looks complete before you start writing down equations. So I have some ball of some mass that attach it to some string of length L, and it's spinning in a vertical circle. So ball is moving with some speed here, and okay, it looks like it has different labels for different parts of the circle. So The V that they gave us, that's for when the ball is at the top here. So this would be one of the snapshots that you have to pay attention to. And the speed V given is for this snapshot. Let me label this snapshot top. Answer the questions below. Okay. And it's asking at the bottom of the circle, how fast is the ball moving? So the question has all the signs of a situation where energy is conserved, negligible friction, and even though the tension force in the string is, it's not a conservative force, but the direction of movement is perpendicular to the direction of tension, so it does not work. So the only force that's doing any kind of work here is gravity, and gravity is conservative force. So you can use conservation of energy and include the effect of gravity as part of the potential energy. So we are going to use conservation of energy. And since we are convinced that total mechanical energy is conserved in this setup, we can say this, that the total mechanical energy in one, so this is the place where you have to identify useful snapshots. So the way conservation laws are useful is it lets you take two different points in a physical setup and say that some physical quantity at those 2 points are the same despite all the interaction and processes that's taken place. So I have one snapshot already identified. And since we want the speed at the bottom, the other snapshot that we should use is this one here. Let me label that bot for bottom. So we say total energy at the top is equal to total energy at the bottom. Very simple. And the rest of the steps are spelling out what different parts of the energy is. Setting up some algebraic expression and hoping that we have the same number of unknowns as the equations and solving for it. So let's go through this here. So breaking out the total energy in terms of the potential energy and kinetic energy, I have gravitational potential energy at the top plus the kinetic energy at the top is equal to the gravitational potential energy at the bottom plus the kinetic energy at the bottom. And let me set some references to make my problem solving simple. So for this gravitational potential energy at the bottom, we can make that zero if we set our reference for the height. So that at the bottom of the swing, we say that's where y equals 0. Then we can say, oh, the gravitational potential energy at that point is 0. We do have freedom to set arbitrary reference point for gravitational potential energy, and we are using that freedom to simplify our mathematical expressions. So this expression is mgh, and as I'm writing down, let me just note in the geometry, the height here, it looks like, looking at this picture, it should be 2L, the diameter of the circle, or twice the length of the radius string. So with that, let me just write out the gravitational potential energy at the top is mg times 2L. And the kinetic energy at the top is 1/2 mv squared, noting that this v is the exact same v that's noted here. So it's not a generic v. That's equal to 0 gravitational potential energy at the bottom and the kinetic energy at the bottom. And I'm going to write it in terms of this parameter that's given. 1/2 mv bottom squared. Okay, so looking at this expression, I have one unknown, the speed at the bottom. And I think I know every other quantity. I mean, mass cancels out, but even if it didn't cancel out, it's one of the parameters I could use. So solve this for velocity at the bottom, and we're done. I'm just gonna do that algebra in my head. You're welcome to pause and work it out yourself or double check my algebra. So after I'm done doing that algebra in my head, this is what I get. Velocity at the bottom is equal to square root of V squared plus 4PL. So let me just put this in the answer box. All right, let's keep going. So that's part A. For part B, it's asking, as the ball moves at the speed given above, what is the tension force on the ball? Oh, yeah, so this is one of those mixed strategy questions, by which I mean it. So we used the conservation of energy strategy for the first part, and the biggest, one of the two biggest reasons we are going for conservation of energy is that it's so much simpler problem solving strategy. So that's how we would like to approach every single problem if we can. But there will be situations when you do have to fall back on the standard strategy. That's whenever they mention force. Usually whenever they mention force. Because to find the force, you usually need to use Newton's law problem solving strategy. So we'll just have to do that. So it's asking the string applies attention. Okay, so I'm looking at this snapshot here, and let me just take a little bit of a shortcut and draw my free body diagram just right on top of this figure. I normally don't do that because I want to avoid confusing my force labels with other things, but I think I've earned the right to do that after having done standard strategy for a whole month. So, and hopefully you also feel more comfortable enough with the free body diagrams that when you have other labels in your diagram, you don't confuse them for force. So when this mess is at the bottom here, so there will be gravity pulling it down, mg, and there should be tension force pulling it up, T bottom. And here's an important question to make sure that you address in your head, which is, what is the acceleration of this ball at this point? And if you are answering acceleration equal to 0, then you need to review circular motion. Whenever something is moving in a circle, it doesn't have zero acceleration. It'll always have centripetal acceleration. That's the important thing that you have to acknowledge, remind yourself, realize before you can do this correctly. So acceleration at this bottom, so it'll be your centripetal acceleration. So it'll be actually even given in terms of other kinematical parameters. It'll be the speed at the bottom, that would be velocity at the bottom, squared divided by the radius of the circle, or in this case L. So we are going to be using this as we write down our Newton's law strategy expressions. So I've done standard strategy. Step number 1, draw free body diagram. So I thought about acceleration, but step number 2 is specifically defining your coordinate axis. So let me define my coordinate axis so that upward is my positive x, and it's just one dimensional. I don't have to include the other dimension. Standard step number 3, breaking down forces into components. No need here. Step number 4, I'm going to write down Newton's second law equations. So this is step number 4 of the standard strategy for part B. I have my net force, which will be tension minus the gravity, mg, going in the opposite direction. That's equal to mass times acceleration, and I already wrote out what my acceleration is. So let me just write that down to simplify some of those steps. Acceleration, v bottom squared over L. Okay. I think I have one equation, one unknown. So this is my one equation, and tension at the bottom is the only thing I don't know. So yeah, I think I can just solve for that. And I'll need to plug in the speed at the bottom as I'm doing that. So let me just do that. So tension at the bottom of the swing is going to be equal to, let me factor out the mass m. So m times speed at the bottom squared, so it will be this quantity, v squared plus 4gl divided by L. Um, yeah, and then from moving the gravity over, I had plus mg vector dot m, so I have plus g. Um, oh, I think I can simplify it a little bit more. I can cancel this L with that L and get tension at the bottom is going to be, let me write it this way, mv squared over L, that takes care of this term. And then the rest will be 4 mg plus mg, so plus 5 mg. Okay. Um, I don't know what more is there. So tension at the bottom, in this case, it's significantly greater than the just the weight of the ball. And I think all of that is correct. Yeah, I'm just looking at something to make sure I didn't miss anything. I don't know. That value just seemed high to me. Maybe after I'm done, I'll just plug in that part B to make sure I'm doing it correctly. Okay. Assuming speed at the top is fast enough that the string remains taut, yeah, what is the tension force on the ball? Oh, I see. I think they want me to answer tension force at the top in terms of the speed at the top. Okay, so let me do that. I thought the otherwise the answer was too simple. Tension at the top equals 0. But that's at a minimum speed v. And for this question, they are not asking for minimum speed v. So so I have to go through the same steps that I went through for part B. So taking this picture here at the top, I need to draw my free body diagram. So let me just draw free body diagram here. I always have gravity, so there will be gravity mg. And this time, tension can only pull, so tension will be downward, not upward. And all this is fine because I remember from my circular motion stuff that acceleration here is not zero. It's a centripetal, it's a pointing downward, and it's a pointing downward with the magnitude v squared, speed at the top squared, divided by L. So let me just write that out. Copy and paste it here, and we'll work out the remainder of standard strategy here. So I've done standard strategy, step number 1, free body diagram, and I thought about acceleration and my defining my axis. Let's define this as my plus x-axis. No forces to break down into components. Everything is already pointing in plus x direction. Now I can write down my Newton's second law equation. Net force is equal to tension at the top plus mg this time because they're pointing in the same direction is equal to mass times acceleration, the centripetal acceleration, v squared over L. Well, I can solve this for tension. Tension is equal to mv squared over L minus mg. I think I'm done. That is in terms of all the parameters that I'm allowed to use. Okay, so that's our answer to the tension force at the top. Yeah, the difference between them is how much tension in the string exists. Yeah, and it does say it's more than by 2 mg, so it is by 6 mg, and let's hope that it's actually correct. So let me go to the question page and just enter this mv squared over L plus a 5 mg to convince myself that it is correct. And I think it is right because it does speed up as it swings down, and that's what the um, the last question part there is getting at. So mv squared L over plus 5 mg. Mv squared over L plus 5 mg. Yep, good. Okay, so that's the question. Wow, that took a while. It's a multi-step question. It does take a while. Okay, the x component of a force on some mass golf ball by 7 hour, I don't care, versus time is plotted. Okay, I'm given force as a function of time. Okay. And it says find the x component of the impulse during the intervals. So this is where we lean on this definition. Impulse is force times the duration of time. Now, we've been using this straight basically under the circumstances where either we had constant force or we were dealing with the average force. It looks like we have some portions of this that's not that. We have a force that's varying as a function of time. So in these circumstances, what we have to do is it's similar to what we did for variable force with the spring force in the context of work and energy. We have to deal in terms of the infinitesimal amount of impulse delivered by the force over an infinitesimal amount of time. And we take the value of force at that exact time. And as long as we make this interval small enough, we can treat force as being constant over that interval. So this is the valid formula for your infinitesimal impulse. Now, they aren't asking for infinitesimal impulse. They are asking for value of impulse over this finite interval, 0 to 50 milliseconds. So we need some way to add up these infinitesimal contributions. So what I have here is basically what contribution due to one sliver here. They want the whole thing. And the short answer there is, I've covered this before in lecture, you have to integrate over the whole interval. That's really the conceptual meaning of integral, and I always like to go through these steps first, because you will find that whenever you encounter integrals in physics, the hardest thing isn't integral. The integral is easy, simple. Hardest part is setting it up. And the thing that will help you set up the integral is first thinking about the infinitesimal portion, the integrand. Once you set up your integral with that, then what you get usually at our level will be pretty simple. So, but this integral, integral is the area under the curve. So that's what we are going to calculate. We're not going to bother with actually coming up with a functional form and finding the antiderivative. Don't need that. That looks like a triangle. So let me find the area of a triangle. And one thing that will help me is, so my units are in newtons and milliseconds on the graph. It looks like they are looking for Newton times milliseconds on the answer. So I don't need to have to do any unit conversion. So this is a triangle of base 50, height 30. I know the formula for that. It's going to be 1/2 base 50 times height 30 units. The way the question is worded, they all just work themselves out. So 750 Newton millisecond. That's what it is. The next, the 50 to 100, that's easier. Base is still 50, but it's now a rectangle. So I can just do 50 times 30 or 1500 Newton millisecond. Okay, and the second part is getting at what we talked about here. It's what the physical meaning or usefulness of impulse is. It gives you the change of momentum. So these answers are basically exactly that. As long as you're talking about, oh, wait, but they went from Newton times millisecond to basic SI unit. So I have to convert milliseconds to seconds. So just doing the unit conversion on the side quickly. So I have something that's in milliseconds. I want that in seconds. So what I'm multiplying here is millisecond on the bottom, second on top. I want this fraction to be 1. So 1 second is 1,000 milliseconds. Okay, so divided by 1,000. I think I can do that in my head. Just put a 0 in front. 1.5. Okay, so that's it. Or at least that should be it. Yeah. Okay. So it says water from a fire hose is directed for, so there's my wall, and it says I have some kind of fire hose that's firing water at a rate of, so there's some kind of flow rate of 46 kilograms per second, and they are coming out at speed of 45 meters per second. And we'll assume that as it's hitting the wall, it has that speed. Calculate the force exerted on the wall, assuming the water's horizontal momentum is reduced to zero instead of bouncing off. Yeah, okay. So now, if as you're looking at it, you're at a pause because you don't have all the traditional quantities you would be given if you were asked to calculate force, like mass and acceleration, that sort of stuff. Um, so this is where our new definition of force is useful, and I think writing it out, we can kind of get a sense of how to make use of the information that's given here. So let me write out the definition of force. That's a change of momentum, which applies if there's only one force, and that one force is responsible for change of momentum, divided by the duration of time. Okay, and it looks so superficially that the question is giving us some kind of mass quantity and some kind of speed quantity that allows to calculate change of momentum. The only challenge is that it's got these time elements to it that's annoying. So when you have a situation like this is what I would recommend that you give it a try. Imagine what happens for some unit time. So even though you are not given delta t, imagine you have some time delta t. And so here I'm going to do it symbolically, but you could even imagine delta t is equal to something like 1 second. If somehow it turned out to be a quantity that cancels out, that it won't matter that you plugged in some number as long as it wasn't zero. And if it's a quantity that doesn't cancel out, then then it's a more difficult question. So we're going to assume that we have some amount of time delta t, and let's see what happens under that. So I can calculate the change of momentum over that delta t, because I will have amount of mass of water that's come out and hit the wall. That'll be the flow rate. Let me call this, I don't know, L. That'll be L times the delta t. And we are given the velocity. So, okay, I think I have enough to write down my change of momentum. That will be the mass, L times delta t, times the change of velocity as an absolute value, unsigned quantity, is going to be V initial minus V final, which is 0. So V initial is just the initial velocity. So that's change of momentum over the duration of time. For the calculation of force, I'm dividing out that delta t. Hey, they cancel. So all I have to do is flow rate times my initial velocity, and that'll give me the force due to the water on the wall. So 46 times 45. 27. And if you work out the units, you can see that it works out to be correct units. Kilograms per second times meters per second is kilogram times meter per second squared, which is unit of Newton. So uh, I won't make the claim that if units work out, it'll always work out, because that's not always the case. But if units work out, there's a chance that um, even if you didn't go through all of this reasoning, that somehow the combination wasn't entirely meaningless. That's one of the reasons we physicists like to pay attention to units, because sometimes they reveal some relationship that might not have been obvious. So this question says a rocket takes off from Earth and reaches some speed that in 10 seconds. Hmm. Wonder if I'm supposed to take into account the gravity during all this, but well, let's see. So we have some rocket of some initial mass m, and it's taking off from Earth, and it's reaching some height. and it's got some different mass, and it's moving at some speed, 99 meters per second, in 10 seconds. I wonder if that's relevant. Let's see. If the exhaust speed is 1700 meters per second, so while the rocket is firing off, this is kind of the midpoint thing. So the way rocket propulsion works is it ejecting fuel with some exhaust speed. And during this interaction, momentum is conserved. So the momentum that's carried away by the exhaust gas has to be balanced out with the momentum change of the remainder of the rocket. So that's how we should approach it. Now, your textbook might have some formula derived. Let me do this based on first principles from scratch. So I'm going to make some approximations, which the system might say it gives a wrong answer. In that case, I will just refine those approximations. The very first approximation I'm going to make is I'm going to assume that all 100 kilograms of exhaust is moving at this speed, 1700 meters per second, in the frame of Earth. Because as the rocket speeds up, that's not actually going to be true because this is speed in the rocket's frame. So in Earth frame, this will actually change over time. But I'm looking at this velocity, it's much smaller compared to that. So I think I'm making a good approximation. We'll see if it results in an answer that the system says is correct. So under this approximation, we can basically treat this as a conservation of momentum question, where this is my initial snapshot, rocket sitting on Earth, zero velocity, and my final snapshot will look like rocket is the remainder of the rocket is moving upward at that speed, and I have downward thing. It's moving as has some mass, small m, and it has this exhaust velocity. And one constraining equation I would have is that the total mass of the rocket should be its initial mass of the rocket is its final mass plus the mass of the fuel burned. Uh, yeah, so we'll be using that. So let me use conservation of momentum. I'm saying momentum is conserved because this kind of looks like a collision type question, interaction happening over a limited duration of time, and yeah, just things happening. Now there's something I'm ignoring as we do. So especially if you're saying momentum is conserved, we are basically saying we can neglect external forces like gravity. Yeah, and so that's a second approximation I'm making. And if the system says my answer is wrong, we'll come back, take a gravity into account, and see if that's what I need to do. So okay, so with those two approximations, one all of fuel ejected all at once, two gravity negligible. This is the equation I would set up. The initial momentum, zero, is equal to the sum of the two final momenta. Momentum of the remainder of the rocket plus momentum of the ejected portion of the rocket. So it'll be its mass times, let me use the sign to indicate the direction of the exhaust, minus V exhaust. Okay, so let's count our unknowns. So looks like we don't know the total initial mass. So, and we technically don't know this. So we have two unknowns. I think those are the two unknowns. I know everything else. Uh, even have this extra information about time. So yeah, I have two unknowns, two equations. I should be able to solve for it. Let me eliminate m prime using this. So I have m prime is equal to initial mass minus the mass of the fuel. So plugging that in, I get 0 is equal to that combination of masses times V plus or let me just pull out the minus sign so I don't confuse myself. Minus small m v exhaust. I think I can solve for this big M. Let me do that algebra in my head. If you need to pause the video, make sure your algebra agrees with my final answer. That is small m plus small m times exhaust divided by the speed of the rocket. Yeah, I think that's right. And I can simplify it a little bit. I can factor out the small m, 1 plus this ratio of exhaust per speed of the rocket. So let me plug in the numbers based on this and see if the system says it's correct. There's a chance that it says it's not correct, and I'll make the corrections for these two approximations one at a time. I don't want to do more work than I need to. So, okay, method of fuel burn times 1 plus the ratio of exhaust, 1700 to the speed of the rocket. Okay, 1817 is what the answer is here. Let me put that in and see if it says that's correct. There's a chance it doesn't. All right. So the first thing that I should correct is, especially because they gave us this time information. Like one way that time information is useful would be it'll tell us the external impulse. So because when you look at this, there's gravity on this whole thing. Like if you're drawing free body diagram of the system, um, then what you have is you have the whole thing, initial mass m, downward mg, and of the whole system, including this and that, there's no other force. Gravity is the one force, so which means this will lead to impulse of force times duration of time, and what this means is the change of momentum. So this leads to modification of this conservation of momentum equation. So we started out with a 0, and so I think the way that's conceptually least confusing for me is to write it this way. Change of momentum. So my momentum final minus my momentum initial should be this. So, mg, big mg times delta t. I have, this is my momentum final. So m plus m prime v plus small m minus v exhaust. That minus 0 is equal to mg times delta t. So I'm writing this out just to see how I need to modify that equation. So if this is staying on this side and staying positive, then this needs to move over. Yes, okay, I need to do plus mg times delta t. And I think that's right. When I add this here, the effect of that is that it tends to like make this smaller. So I think that makes sense. Yeah, okay, so here having put all this in, yeah, I think I can keep that plus, so plus mg times delta t. So let me collect all the like terms on the right hand side. That's going to be mv plus mg times delta t, and collect all the other terms on the left hand side, moving this over. That's mv exhaust, and then move that over, plus a small mv. Okay, so on the right hand side I can factor out m. So I have v plus g delta t, divide that out to get m. So my final expression for m from all that is mv exhaust plus mv divided by v plus g delta t. Okay, so let me plug in the numbers there. I don't think I'm going to try to simplify that. Seems not really possible to simplify. Okay, so I have 100 times exhaust speed 1700 plus, again, 100 times the rocket speed 99 divided by rocket speed 99 plus g 9.8 times delta t 10 seconds. Okay, so we have 913 point. Wait, that makes um must have done something wrong. Oh, sorry. As you might notice, I haven't done a lot of these rocket propulsion questions, and um, which is my excuse for not having all that good of an intuition for this type of questions, because the intuition is a product of your experience, and whatever you don't have a lot of experience with, your intuition is gonna be weak. So I thought when I have this influences added, that should make the initial mass of the rocket larger. That's what I intuitively thought, and I think that intuition is wrong, because it comes down to the amount of fuel burned should be a greater portion of the rocket if there's something pulling the thing down. So to make this 100 kilogram greater portion is to make the initial mass of the rocket smaller. And just to finish correcting the mistake, so somehow I guess when I was writing these equations down, I made two mistakes that canceled out. I forgot to write down minus sign here, and when I moved this over, I forgot to put a minus sign on. That resulted in the correct sign here, but it's two sign errors canceling each other out, which is what you should aim for. So yeah, this is the question. So I have corrected for gravity. So apparently that's significant. I need to correct for that. And I think this one, it must not be significant. I don't know if the programmed answer actually takes that in. Yeah. So programmed answer, if I had to guess, it probably uses a formula from textbook and actually takes into account this approximation that I made. And the reason that approximation is good is, well, this is so much bigger than that. So, so that's really the justification for approximation. And the trial here is that you still resulted in an answer that's within 1% of the correct answer. So now, if we are looking at rocket reaching higher speed, then we would have to account for what I didn't account for this time around. So this question says the figure below shows bullet of some mass. Let me just start doodling and just writing down symbols so that I understand what information is given to me. Bullet of some mass traveling horizontally toward the east with a speed, let me say V naught for initial, which strikes a block of mass, let's say capital M. That applies both the description up there and the figure here. That is initially at rest on a frictionless table. Okay, seems simple enough. Moving at some speed V naught. After striking the block, the bullet is embedded in the block. So for the kind of post-collision picture, what we have imagined is you have the block and you have the bullet that's been embedded, and I think they're going to be moving together at some speed of V final. So have that picture in mind. Embedded, move together as one unit. What is the speed of the block/bullet combination immediately after the impact? So hint will probably ask you to consider the conserved quantities. So we are deep into conservation law strategies. And when you are applying conservation law, so we don't have kind of fixed set of steps that I've given you like with the standard strategy, but this is what I might recommend. As a kind of first or maybe even zeroth step, you should identify the conserved quantity. And at this point in the semester, it's super easy. You basically have two choices. You could be conserving energy, or you could be conserving momentum. And later on the semester, you could potentially be conserving angular momentum. But right now, energy or momentum. And in the lecture, you've been told the conditions that's necessary for conservation of energy and momentum. For energy, the condition you need is no net work by non-conservative force. And for momentum, the condition you need is no impulse due to external force, or I guess net external force. Now, having said all this, there's one other thing you have to be careful when it comes to energy conservation. Sometimes the problem won't explicitly tell you you have these non-conservative forces. So you need to kind of figure it out from reading the question. And for this question, the biggest hint is where it says the bullet is embedded in the block. And what that means is this is what we describe as a sticking collision. And in sticking collision, energy is not conserved. It's an inelastic collision. In fact, it's what we call completely inelastic collision in the sense that it loses as much kinetic energy as possible. So if you remind yourself through all this, then what you should realize is, so in this question, only momentum is conserved, assuming no net external force. And looking at this, especially because they told us frictionless table, there is external force, gravity and normal force, but they balance each other out, so no net external force. And I will tell you, even if the table hadn't been frictionless, a lot of times we would come up with an argument why friction can be neglected. Maybe the impulse due to friction is negligible compared to the impulse due to the interacting forces. So we've identified the conserved quantity, momentum. Then the first and maybe the only step is you write down the conservation law statement. So state the conservation law. By which I mean, you say your initial momentum, the total initial momentum, is equal to total final momentum. And the rest, hopefully, you remember the definition of momentum, and you can write those down in terms of the quantities that are in the problem. So let's do that. So the definition of momentum is mass times velocity. So for initial picture here, or snapshot 1, before the collision, you have momentum of the bullet, mass times V naught, plus the momentum of the block, which will be 0, but let me just write it out for clarity. Big mass times 0 for the velocity of the block. That should be equal to the final momentum, final total momentum, which, let me say the total mass of this combined object is the small m plus big M. Treat it as just one object. Small m plus big M, which is moving at speed of v final. So this is one equation in terms of one unknown v final, which is what we are looking for. So let me do that algebra in my head and write it down here. V final is equal to small m divided by the sum of the masses times v naught. If you want to double check my algebra, pause the video, do it for yourself and make sure I didn't make a mistake. And I'll plug in all the numbers all at the end and just type it into the homework system to make sure I didn't make a mistake. Okay, part B. What is the magnitude and direction of the impulse by the block on the bullet? Okay, so let me just doodle a little bit to make sure that I understand. So we are thinking of the kind of what's happening in the process of the collision. So bullet is trying to getting embedded. So I can draw free body diagrams for this bullet and the block. The free body diagrams would look like the bullet, it's slowing down, so there must be an applied force this way. The block is speeding up to the right, so there must be applied force that way. And this should be action-reaction forces. There are internal forces, and of course, there are other forces like gravity and normal force. But I'm just ignoring all those because they balance each other out and they don't affect anything. So the direction of impulse by the block on the bullet, that's describing this. So here it must be leftward. Then the block exerts an impulse. For the impulse, you have to know the definition of impulse. Impulse, sometimes indicated with the letter J. I just never got used to it, so I'm just going to spell it out. Impulse can be written two different ways. It can be written as, this is the definition of impulse, force times the duration of time. Now here, this won't help you because you don't know force, you don't know duration of time. So the other description of impulse that's helpful here is the impulse as the change of momentum. So here you can figure out the change of momentum of the bullet. So the change of momentum of bullet of mass m is going to be its final momentum minus its initial momentum, which is its final speed. Let me write out the answer we had from A. Let me just keep it as a symbol. Because as I plug in the numbers, I'll have a numerical value. I'll just remind myself to use that. So it'll be mass of the bullet times its final speed, whose numerical value we know from part A, minus speed of mass of the bullet times its initial speed, V naught. So doing simple simplification, the expression for the impulse on the bullet is the absolute value, factor out the mass, times the V final minus V initial. I'm putting the absolute value because I think if you put in a negative number here, which I think my final number here will be, system will say this answer is wrong because you already indicate the direction here. It's not expecting you to double indicate the direction. Okay, the magnitude and direction of the impulse from the bullet on the block. Now, I could go through this calculation again if I want to. I actually don't have to. If I believe in the conservation of momentum, which comes from Newton's third law, I know the answer here is the same as B above. So I don't have to redo this calculation using the mass of the block. Don't need to. I trust in Newton's third law. I trust in conservation of momentum. So I'm just going to use the same answer as B. Now the direction will be rightward. Again, because I trust in the Newton's third law when the conditions are met. So I'll simplify the calculation, just use the same number for C. Part D, if we took 3 milliseconds for the bullet to change the speed from the initial speed, yeah, it's just stating it twice, not a different number, to the final speed after impact, what is the average force between the bullet and the block during this time? So this is where actually this relationship is helpful. So we already figured out the impulse. So using the thing on the far right. So all we have to do is solve for force and we are done. We are now given delta T. So let me solve that for force. The force is change of momentum or the impulse divided by change of time. Yeah, and I guess since we will have the change of impulse from parts B and C, let me just write it that way. The magnitude of the average force is the absolute value. The change of momentum from B and C above divided by the duration of time that the question here gave us. And I'll make sure I put in a positive value because the question is asking for magnitude. Okay. Of the kinetic energy initially present in the bullet, what percentage still remains as a kinetic energy of the block/bullet? Oh, okay. I think I just have to do the calculation. So I'll break up the calculation this way. I can say the final kinetic energy is going to be 1/2 the total mass, the sum of the masses times the V final squared. And the initial kinetic energy is equal to 1/2 the small mass of the bullet times its initial speed squared. And for this percent remains as kinetic energy, 100 times Ke final divided by Ke initial. Yeah, and I'll get a numerical answer and plug that in. So yeah, let's get all the numbers. I'm gonna just use regular calculator here because I think switching between Wolfram Alpha and this screen, I can anticipate them being super annoying. So let me just use regular calculator. I'll just keep everything in basic SI units. I'll do some conversion as we go. So the masses, I'm gonna convert 70 grams to kilograms, so 0.07 kilogram. So 0.07 kilogram divided by sum of that with 4.5. I can do that in my head. So 4.57 kilogram, that's the ratio of masses, times 300 meters per second. I'm gonna keep an extra significant figure because I will be using this number in later parts. So I'll write down 4.595 meter per second. For the grading system, all that's required is only the 3 significant figures, but I want to be extra sure that rounding error doesn't affect my answers later. So the magnitude and direction of the impulse by the block on the bullet should be the mass, 0.07 kilogram, times the parenthesis open, 4.595 minus 300, parenthesis close, is equal to minus 20.68, or absolute value, so 20.68. 20.68, and because I kept everything in basic SI unit, I'm guaranteed that this answer should be in basic SI unit. And it'll be the same answer for part C, nothing's changing. I already indicated the directions. So for part D, so I have this, I'll just leave it as minus and just remember not to write it down. I have this impulse from parts B and C. I just need to divide by the time. So I need to divide this by not 3, but 0.003 second. That's the 3 milliseconds. So 0.003 second or 3 millisecond. And that should be, yeah, pretty large force. 6,890 Newton. 6,890 Newton. I'm keeping only 3 significant figures because this is not going to be an intermediate number anywhere. So, all right, that's D. For E, so I need to calculate the kinetic energy first, and then I'll do the rest. So for kinetic energy, the final kinetic energy is 0.5 times the sum of the masses. Oh, I think I remember 0.457, I think. Is it? Yeah, 0.457. 0.457 times the final speed. I have that here, 4.595. 4.595 squared is equal to, this should be in joules, 4.825 joules. And I'm keeping 4 instead of 3 significant figures again because this is an intermediate number. I want to be extra sure rounding error doesn't affect my final answer. So for the initial kinetic energy, it should be 0.5 times the mass, which is 0.07 kilogram, times the initial speed squared, 300 squared. So 3,150 joules. 3,150 joules. Let me double check. Now, it shouldn't surprise you that initial kinetic energy is bigger than the final kinetic energy because, you know, in inelastic collision, you lose energy. It might surprise you just how big the discrepancy are, but I think it makes sense. If that block had been of an infinite mass, it would have lost 100% of energy and would have had a 0% of energy remaining. Now the mass isn't infinitely large. It's only what, like, I don't know, a little less than 100 times as large as the bullet. So, so I think this amount of energy loss makes sense. So let me calculate the percent of energy remaining. That should be 4.825 divided by 3,150. Very small number multiplied by 100 for percent, 0.153%. I think that's right, 0.153%. Okay, let's just plug in the numbers. Make sure I didn't make any mistake, or, you know, if I did, fix it. All right, so let me just copy over those numbers. 4.595, 20.68, leftward. Oh, it's not an option. Did we talk about east is right and west is left? So I'll say westward. And then same number, this time eastward. So the force here is 6,890. Kinetic energy 0.153%. And not a typo. Let's hope that everything is correct. I missed something. What did I miss? Um, no. Did I make a mistake? Um, I mean, the expressions are right. Let me do this on O from alpha in case I made a typo, maybe. Um, it's always possible. I could have made a mistake on the calculator. So let's say zero point 0.5 times 0.07 plus 4.5 times speed, which 4.595 squared. Oh, I definitely did make a mistake because that's 48.25, not 4.825. Okay, that means I think I made a factor of 10 error. Yeah, not sure how that happened, but let's fix that factor of 10 error and let's hope it's graded as correct. Yeah, I don't understand where in the calculator I made a factor of 10 error, but it ultimately doesn't actually matter. So, and I don't have calculator history to go back and make it. So let me just fix it here. So, not here. Let me start here. So yeah, that's this question. If it's got a lot of parts and it asks you to understand all the connections between impulse and the force, and it's not that difficult of a question. It's just long and it um, requires you to remember all the definitions relating to sticking collisions. All right. So this question says, some math child is coasting at some speed. Um, let me say m naught, v naught over flat ground in a 4 kilogram wagon. Oh, okay. I gotta subscript this differently. Let me say this is m child, and I think this is gonna be a common speed, so I can leave that alone. This is the mass of the wagon. The child drops a 1 kilogram ball, so mass of the ball out the back of the wagon. Oh, that's interesting. So that the ball is at rest on the ground. So I have a velocity of the ball, um, final, that's going to be 0 with respect to ground. Okay, what is the final speed of the child and the wagon? Oh, all right, so let me draw the picture to make sure I understood it correctly, and then we'll work through the question. Sorry, I thought this was going to be a trivially easy question, but it's not going to be, which is fine. I don't like trivially easy questions. So I have to describe all the elements of the system that we have. We have the wagon, so let's call this mass of the wagon, which is traveling at some speed v naught. And inside that wagon, we have a child with the mass of the child, and we have a ball. And so this is the kind of the picture that we are starting from. And at some later time, this is the situation we are going to end up with. The cart and the child will be traveling together still at some speed v final that we are going to want to solve for. And the child has caused the ball to go out of the wagon. And this is the part that surprised me. That speed of this ball is 0. Oftentimes, sometimes the questions like this says the child drops the kilogram ball out the back of the wagon and just stands it there, or drops it. And usually, in a real physical situation, when that happens, when you're in a cart and you just drop something to the side, then what that'll do is the thing you're dropping, it'll be moving together with you. And in that situation, you say, "Oh, this is V final, it's V initial." You didn't actually change anything by dropping stuff out of the car, because yeah. So, but the question is written in a very strange way that actually makes it not trivial easy. So let's actually work it out. So So this will, let me just circle this as the second state of things that we'll consider. These are going to become my snapshots, my snapshots 1 and 2. This, I don't know if I would describe this as a collision question. Let's just say we didn't somehow identify this as a collision question, which if we did, it'll simplify some of the steps. So I'm just considering this picture de novo from the start. And as I'm doing that, I'm thinking, what kind of problem solving strategy can I apply here? And my number one choice, almost always from this point on, throughout my entire physics career, will be, can I use conservation strategy? So I'm considering conservation law strategy as a possible way to tackle this question. So the very first step in conservation law strategy is you need to identify conserved quantities. And it helps me to list all the quantities that we know can be conserved. There's conservation of energy, potential and kinetic energy. And really, when we say energy, we mean mechanical energy, because we are not dealing with other forms of energy in this class. And so far, we've covered the momentum. So those are the two quantities that could potentially be changed, potentially be conserved. So in this first step, we are testing, can they be changed? If they can be changed, then we would say, all right, that quantity is not conserved. So for conservation of energy, the condition that you are looking for is no net work by non-conservative forces. And we have only two conservative forces in this class, gravity and spring force. So basically any force that's not a gravity or spring force better not be doing any work. If they do, then there's a chance your energy wasn't conserved. Unless that work was done only to transfer energy from one object to into the other, but that's a separate thing. And momentum, the condition that you are looking for momentum conservation is no net impulse um, due to external forces. And in lecture, I go into more detail of justifying these two expressions. I just want to highlight here that this is important. Every single word here is important. Every single word here is important. And really, the thing that trips up a lot of people is what kind of forces to watch out for. When you're dealing with the energy, it's the non-conservative forces you worry about. When you're dealing with the momentum, it's external forces that you worry about. Don't swap them around or mix them up, please. So with energy, I want you to visualize this setup. So guess gravity isn't actually doing any work here. So all right, there's no uh, and there's no spring, so no spring force. I don't think there's any normal force doing work here. So as you look at this picture, it might be relatively easy for people to think, oh, that means energy is conserved because it feels like there's no force that's doing work. That's where I want you to be careful and think through this picture carefully. Think about the moment when the child is pushing the ball out. And in order to achieve this final state, I believe the child has to really throw the ball. And as the child is throwing the ball, okay, now somebody's doing work on the ball. Where does that energy involved in the throwing comes from? And as you think through it, and so the force that the child is applying on the ball, that's an applied force. It's one of the non-conservative forces. And really the energy that the child is throwing the ball with comes from the chemical energy, the food energy. It's not one of our mechanical energies. So when you think through this picture carefully, you should conclude that energy is not conserved in this setup because there's a person who's throwing stuff that additional energy has to come from that person. It can also go into that person. If I'm catching a ball, as I catch the ball, I dissipate the mechanical energy into friction and whatever. So So it's important. This the first step is it's important like free body diagram drawing step is important. If you do this step wrong, the rest of your strategy will be wrong. So okay, I have argued to myself that energy is not conserved, so I'm not going to be using conservation of energy. So the question is a momentum conserved? Well, this applied force, it's an internal force. If we include the ball as part of our system, then then it's a then it's internal. It's a force between the two objects in the system. So there's this impulse that the child is imparting to the ball. Well, it's internal force, so it's all accounted for. Total momentum is still conserved. So I'm going to say, okay, my momentum is conserved. I'm going to write conservation of momentum energy, and let's hope we have enough equations to solve for our unknowns. So once you've identified your conserved quantity, then the next step is write conservation law equation. So as you're doing that, you should identify useful snapshots if you haven't already. Here, I've done it already. Snapshots 1 and 2, initial and final. That's kind of common choice. So going with the choice, let me write down my conservation law equation. So I'm saying net momentum, the total momentum in snapshot 1 is equal to the total momentum in snapshot 2. All right. And the next step, which I won't bother to write out in detail, is I'm gonna identify, okay, what are the constituents of that total momentum, and do I have enough equations, and go through that. So total momentum is snapshot 1. So I'm going to use the common speed, but let me just split out each object separately since they are listed out separately. So I have momentum of the child, plus I have the momentum of the wagon, plus I have the momentum of the ball. They all have the same speed because they were traveling together. That's my snapshot 1. And since total momentum is conserved, the total momentum in snapshot 2 must be the momentum of the child in that snapshot plus the momentum of the wagon in that snapshot. We final same speed for child and the wagon plus momentum of the ball in the snapshot, which according to the information given is going to be zero velocity at rest on the ground. It's a weird setup, but that's what the question is telling us, so we'll go with that. So all the masses I believe are given. V1 was given. So the only quantity that wasn't given that we have to solve for is V final, and we have one equation, one unknown, so it should be solvable. So the rest of the steps in the solution is really finishing the algebra. And as I did with the previous question, let me just use my computer algebra system. I'm feeling lazy, hungry, tired. So I have my equation. I did a part that computer algebra system can't do for me. I'll let the rest be done through the calculator. So mass of child, V1, mass of the wagon, mass of the ball, V final. I think those are all the symbols I need. I might have defined them already, but declaring it multiple times doesn't hurt anything. Let me define my equations. That's going to be MC times V1 plus mass of the wagon times V1 plus mass of the ball times V1 is equal to mass of the child times V final plus mass of the wagon times V final plus, let me just write 0 because that's gonna what the final term is gonna be. So that's my equation. Let's just make sure I typed it in correctly. Everything looks fine. I'm gonna use solve function, solve this equation for V final. And oh, there it is. That looks right. It looks complete. I don't know if it's right or not. It's probably right because it looks complete. Let me put this a solution, last output, of first element of the last output into its own variable so that I can do a substitution of the numbers that we've been given. So the numbers we've been given are the mass of the child, 23 kilogram. Initial, oh, I labeled this V not, but it's V1. Just if you somehow just used a couple different letters. Make sure you know what's what. Mass of the wagon is 4 kilogram. And mass of the ball is 1 kilogram. And we final we are solving for, I think that's it. Yeah, let me make sure it does the decimal approximation. All right, so V final is 3.42 meter per second. That's higher than initial number. I think it's worthwhile just pausing for a bit and making sure that that makes a sense. That so when the child is doing work on the ball, the child is actually doing negative work. Oh, but there's a reaction false on the child. So that must be doing some positive work. And somehow that's, I guess maybe not in terms of doing work, but in the sense that, if that child was hungry and restless, not restless, as hungry and tired as I was, he might not be able to throw the ball hard enough. So this act of throwing the ball requires energy. So I think it makes sense to me that this final speed of this child in the cart is higher. And somehow if we calculate the total energy of this thing, I think it's going to come out to be higher. Okay, so let me put that in as the answer and see if the system says that's correct. 3.42. All right, it says it's correct. So I must be not right. Okay, actually, so before moving on, let's just try calculating the kinetic energy of the thing for fun. So I'm just gonna use that number. So, initial kinetic energy would have been the total mass, well, times 1/2 times V initial squared. And let me substitute in all these numbers that I've typed it in before. So this was your initial kinetic energy in units of joules. And let's see what this looks like in after post collision or post throwing of the balls. So child and the wagon is traveling at the speed of a final. Let me put in that answer from before. And I guess I can just leave it there. If I included a explicit term for ball, it would have been 0. So when I do that, yeah, I get 158.1 joule versus 152.5 joules. So energy has gone up. So it was good that we didn't use conservation of energy because that would have been wrong. Let me just say I used the computer algebra system for the win. All right. So it says two cars approach an icy, so it's telling us no friction, four-way, so that's the 2D part, perpendicular intersection. Car, okay, let me start drawing this picture here. So I'm gonna draw my axis so that this is my plus x is east and my plus y is north. Car A travels northward at some speed VA, and car B is traveling eastward at some speed VB. And the question isn't giving us the speed of VB, but what they are telling us is that after the collision, they stick together. This is one of those sticking collision. And this whole mass of the thing that's stuck together version of the cars, they are traveling at 30 some theta degree north of east. Okay, so let me label this correctly. It's going in some direction here, and the given angle is this angle here. Okay. Oh, and you may assume the cars have same mass. So let me just use the symbol M for both of them. Okay, so it's a collision, and because all the bodies that are interacting are part of our system, so all the significant forces are internal forces. We can say in this collision, momentum is conserved. So we'll be using conservation of momentum. And as you're using conservation of momentum, the thing to be aware of and keep in mind is that momentum is a vector quantity. And because so often we set up one-dimensional situation, it's easy to forget that. But when we say that the momentum is conserved, like the total momentum of before picture is equal to the total momentum of the after picture, this vector symbol is serving as a reminder to tell you that this one equation is actually multiple equations, two or three equations, depending on your number of dimensions. So in most questions, we set it up as a one-dimensional thing so that you don't have to consider the other two dimensions. But in this question, it's now set up as a two-dimensional interaction. So we have to remember that what this equation really means is the total momentum in the x direction before is equal to the total momentum in the x direction after. These different components are individually conserved. And the same deal for the y direction. Total momentum in the y direction before is equal to the total momentum in the y direction after. It's easy to forget that because you don't see that often. And with the energy is a scalar. So with the energy, it's just really one equation. But with the momentum is a vector. You have to remember that these different components are independently conserved. So let me write this out. I guess it's a bit unusual enough of a setup that I think it's worthwhile to just write things fully out and try to identify some of the unknowns that we need to label. And let me just label this a V final so that I have something to refer to. So, so just looking at this interaction here, and so if this were a forced question, there are some steps that's been pre-laid out that I can go through, our standard strategy. And even though a lot of what we'll do now will mirror what we do in standard strategy, since it's technically involving different things, momentum, let me just wing it, do things as we go. But I am going to have this diagram in mind so that I can remind myself of the things that we need as we go. So I'm going to write down the total x momentum before the collision. So before the collision, the car B was moving in the x direction, and it was the only thing moving in the x direction. Car A was moving in the y direction. So I'll say x before will be mass of B, m, times its speed. That will give me the total x component of momentum. That's equal to, I'll write the right-hand side after. Let me just do the before picture first. So the total y momentum before, so only car A is moving in the y direction. So I'll say mass of the A times its speed or velocity. It's going in the plus y direction. So that's the total y momentum before. Nothing else is moving in the y direction. Now, after the collision, you have this one total mass, mass of A plus mass of B, moving in some diagonal direction. So here is where I'll have to think about breaking up the momentum into x and y components. So I have this triangle, hypotenuse, right angle, triangle. So I need to break up this momentum into components. Very similarly, how we, in step number 3 of Newton's law strategy, we break up forces into components. So we need to do that. Let's do that. So, I'm given this angle theta. So this side here, that's going to be the magnitude of the final velocity times sine theta. It's the opposite side. And this component is going to be magnitude of the final velocity times cosine theta. It's the adjacent side. So with this labels in mind, now I can write down what is the total momentum after the collision. So I have total mass, that would be mass of A plus the mass of B times the x component of velocity. So V final times cosine theta. And for the y component, I have something similar. Total mass of A and B, they are moving together, times the y component of velocity. V final times sine theta. Okay, I have two equations. Let me, before I go on further, let's just do a check. Do I have equal number of equations as unknowns? So let me just go through each of these quantities. Mass, I know, or I have a sense it'll cancel out. So I'll assume I know the mass. VB, oh, I don't know this. Okay, I gotta figure this out. That's one unknown. Mass, I know, or I think it's gonna work itself out. V final, I'm not given V final, so I don't know that. Second unknown. Theta, I'm given theta, so I know that. At mass times VA, I'm given VA, okay, good. And everything here is something that I've already counted. Okay, so I have two unknowns. So I think I'm beginning to see here. This equation one would be nice for solving for VB. Here's just one challenge. I don't know the final speeds. If I know final speeds, then I can just solve for VB out of this first equation. But since I don't, I need to eliminate VF as one of my unknowns. And I can do that using my second equation here. Let me solve this for VF. So using that, I can work out an expression for VF. And just doing it in my head, pause it, and do what you need to do the algebra on your end, and divide by 2m times sine theta times 3a. M's cancel out. Okay, that's my expression for VF. And I can plug that in here, eliminate it, and solve for VB. And technically, I think I have enough information to work this out numerically. But you know what? Let me just demonstrate the algebra. Because that's what I usually preach. You know, you need to build up your algebra skill, and so I better practice what I preach. So I'll just work out answer for VB algebraically, just one shot. No, going through other numerical parameters. That also helps avoid any rounding issues if there are any. So let me do this. I'm going to solve it for VB and then just plug in for VF. Normally that may not be a good idea, especially if this VF is a function of VB somehow, but it's not. So I think I can do that without any problem. So solving for VB, I have VB is equal to, masses kind of cancel out. I have 2 times V final times cosine theta. Let me plug in V final. Then I get 2 times VA over 2 times sine theta times cosine theta. And you see some simplifications here. 2's cancel out. That's nice. Um, yeah, that's really one of the upsides of working things out algebraically. Sometimes you see unexpected simplification. And I can combine sine and cosine theta using sine theta over cosine theta is equal to tangent theta. So I can say this whole thing is equal to VA divided by tangent theta. That helps me reduce how many numbers I need to plug in. So now I can plug in the numbers. I have a VA that's 29 meters per second. 29 meters per second divided by tangent theta. So 38 tangent is equal to 37.1 meter per second. And that's it. Since I have the number, let me plug in and check. So it's I hope as you're doing this question, some of it reminds you of the two-dimensional things that you're doing in the standard strategy, and all those skills that you developed as you're working through the force questions. They continue to be useful because we continue to use vectors for a lot of stuff. So this is a question that involves, as the hint when I was hovering over earlier, hint was saying, it involves more than one conservation law. It involves conservation of energy and conservation of momentum. And I actually have a demo that I like to do in face-to-face class. So here, momentum is conserved because this ramp is free to move. And the reason, the way this ramp moves is because of Newton's third law. As this, so this is how the forces work out. Now, you don't need this for this particular problem. So as this cart is on this ramp, here are the forces on that cart. There's gravity mg, and there's a normal force and pushing on the cart that way. So when you look at the force on the ramp, there will be gravity pulling it down. And there is a normal force on that from the floor underneath. So and big M. And there's a reaction force pair to this normal force. So there's a normal force pointed that way. That's the reaction force pair of that. That's why the ramp moves to the right. And in the context of chapter 9, what that means is the total momentum of this entire system is conserved. That's why you have this ramp moving to the right, and you cannot ignore that. So yeah. So in trying to solve for these two velocities, velocity of the cart and the velocity of the ramp, we are going to need to use a problem-solving strategy where we recognize both of those conserved quantities, energy and momentum. And I think I'm just going to use the snapshots that are kind of naturally given to me here. So I'll use this as my snapshot 1, or quote-unquote initial, and use this as my snapshot 2, or quote-unquote final. I think that's a kind of natural setup. And because the momentum and energy are conserved throughout the entire setup, I don't think I need to break it into different parts. Like I don't need to look at, when the cart is at the bottom, and then, so I don't need to do that. I can just take the whole thing as a whole. All right, so let me, so I think looking at the situation, it's clear enough that energy is conserved, that there is no non-conservative force that's doing work on the system. Now, there's this tiny matter of the normal force, which is apparently doing work on the ramp and the cart, because that's the only way ramp would move. But the function of this normal force is it's basically transferring energy from cart to the ramp. So as long as you are considering the entire system, the normal force does not cause the system to lose energy. So I can kind of ignore the fact that normal force is doing work. And there's no friction force. And gravitational force, although it's doing work, it's a conservative force. The work done by gravitational force is accounted for in change of potential energy. So let me write down conservation law equations. So I'm going to have conservation of energy. And let me kind of skip some of the other steps that I was doing earlier where I'm writing down total energy. Let me just write them all down. I think it's just quick enough to just write it down. So total energy in snapshot 1 is equal to total energy in snapshot 2. So by total energy, we mean potential energy plus the kinetic energy, and potential energy plus the kinetic energy. And here the situation is set up so that the only potential energy we are dealing with is gravitational potential energy. And now I'm kind of writing this in a schematic sense, because when you are starting to write down the real expressions, as in where you can actually plug in numbers to, you have to keep in mind that you have two separate objects, and it's important to write down energy expressions for all of them individually. Now I'm going to use a bit of a simplifying convention, which will allow me to not write down things that I don't need to write down, is to say that this ramp, it has gravitational potential energy of 0. I'm kind of defining my coordinate system in whatever way I need to, so that I can say that in the snapshot 1, the ramp has 0 gravitational potential energy. And because the ramp is not changing in height, that'll allow me to say that its gravitational potential energy remains at 0 here. So that'll kind of simplify my expression a little bit. And this cart here, it's at height h, so I'll need to account for that when I write down my potential energy. It's going to have potential energy of mgh at the beginning, plus, for the kinetic energy, I think all I need to do is acknowledge that it's 0 at the beginning. The cart is at rest, the ramp is at rest, 0 kinetic energy all throughout. The total energy final, so I guess when I wrote down mgh, I'm kind of implicitly saying that the potential energy of the cart at the snapshot 2 is equal to 0. So I'm going to say just the 0 potential energy at the end. And here for the kinetic energy, I have to be sure to write them separately. Kinetic energy of the cart and kinetic energy of the ramp. So plus 1/2 mass of the cart times its speed, v sub c squared, plus 1/2 mass of the ramp, v ramp vr squared. So this is the expression for conservation of energy. Now I need to write down conservation of momentum. Let me do that. So conservation of momentum, so the way all the conservation laws are written down are the same. You have the conserved quantity, and you start out with a statement that the total of that quantity at one part of the snapshot is equal to total of that quantity in another part of the snapshot, snapshots 1 and 2. And in snapshot 1, the total momentum is easy to calculate. It's 0 because nothing is moving. So I have 0 is equal to the total momentum at the end. And my own practice for problem solving is I like to write down my equations in a way where all my symbols are positive quantities, or at least they are expected to be positive. So that's what I like to do, at least with the physics 4A type problems. And the reason I like that is it allows me to spot quickly when I have a quantity that's unexpectedly negative. So let me do it that way, and then I will kind of to tell you a little bit of caution in terms of electronic problems, homework systems. So here, as I'm writing down total momentum in snapshot 2, I see my cart is moving to left, and I'm going to say that's moving in the negative direction. So I'm going to write down for the momentum of the cart, minus mvc. And what this minus sign represents is that I'm trying to make this speed, so vc represents the speed, a positive velocity. And you don't have to do it that way, but this is how I like to set up my equations, so that if ever any of my quantities they don't have expected sign, I can spot that quickly. Okay, so the momentum of the ramp, it's moving to right, so I'm going to write down plus mvr. So, so those are all my conservation law equations. At this point, I like to count all my equations and all my unknowns so that I know I have all the necessary information to finish solving this question. I have 1, 2 equations, and let's see. So I'm given the masses, and I'm given the height. So I should and I guess my unknowns were given. My speeds are unknown. So yeah, I have 2 unknowns, 2 equations. I should be able to solve it. It's a matter of algebra. And kind of staring at it for a second, I think what's the easiest thing for me to do is, let me do this first. Solve equation 2 in terms of one of the velocities. That'll let me use that solved for velocity plug that into equation 1 and solve systematically that way. So let me solve, I want to get rid of the velocity, speed of the ramp. So let me solve this for speed of the ramp. So solving it for VR, I get, so I'm imagining moving this over. So I have small m over big M times VC. I think that's correctly solved for. Make sure to check it. So with that tool in my hand, I'm going to eliminate VR from all my expressions. Let me move equation 1 here. And I'm going to be substituting in that expression for VR. That'll get me to this place here. mgh is equal to 1/2 mvc squared plus 1/2 capital M times VR squared, which is going to be that thing squared. So small m over big M squared times VC squared. Oh, wow, I think it's relatively easy because I only have a VC squared term. I can solve for VC and then take the square root. So let me just go through that solution step. So let me imagine factoring out VC from both the terms. Then what I get is VC squared times 1/2 M plus, let me simplify this here. It's going to be M squared divided by 2. 1 factor of M cancels out with that. So just the 1 capital M. I think I can actually factor out 1/2 M to make my expression a little bit prettier. VC squared over 2 times M, 1 plus, I think that's small m over big M. And I move everything else to the left-hand side, or the side where MGH is. Solve for VC. Let me do that here. Doing that, I get this. VC squared is equal to, I think I have a 1 factor of M canceling out. It's nice. So I have 2GH on the numerator. 2GH divided by this quantity here. 1 plus ratio of the masses. Small m over big M. I think that's everything. So if I take the square root of both sides, then I can get rid of the square here. So all right, that's the speed of the cart. Seems reasonable. And there's a kind of a sanity check that's useful to do, which is, and one of the ways you can do a sanity check is to kind of think of limiting scenarios. Here, a limiting scenario is where you imagine that the capital M is much larger than a small m, or it goes to infinity, or I guess more realistically, it's much larger than small m. In that case, this ratio goes to 0. So your solution for speed of the cart goes to square root of 2gh. And when you see that, I hope you recognize that as kind of a speed of something that's fallen down from some height h. And that this answer actually makes sense. If the ramp is so heavy that it doesn't move, then the speed that the cart would have is that square root of 2gh. So that's a kind of a sanity check, making sure that this answer here is compatible with other simpler answers that you know in a simpler situation. So at this point, I think it's easier to just plug in the numbers. And once I have number for VC, I can plug that in for VR to get number 2. So let me just plug in the numbers with the calculator. So I have, let me calculate 2GH first. 2 times G, 9.8, times H, 2.75. That's my numerator. That's going to be divided by, parenthesis, 1 plus the ratio of the masses. 1.5 over m, parenthesis closed. That's what's under square root. So let me take the square root of that. 6.439. I'm just keeping some additional significant figures because that never hurts. So 6.439. It should be meters per second. I kept everything in SI unit. So I'm gonna plug that into here. That'll get me, so I guess I have that value there already. So I'm gonna use that, multiply that with the small m, 1.5, divide by big M, 5. That gets me 1.9317. You can just keep, usually 3 sig figs and you should be fine. So let me plug in those answers and see what I get. Speed of the cart is 6.439. Speed of the ramp, 1.9317. And when you submit it, you see, oh, it says, does this have the correct sign? And that's where you read the question carefully. It's asking for the velocities of the ramp and the cart. So velocity is the vector quantity. They want you to indicate direction. And I guess in this question, there's nothing that where you're indicating direction. So I guess they want you to use the sign to indicate the direction. So, so it's a kind of a feature of an electronic system. If you are doing this on exam, like if I'm able to see all your work, then whether you have positive here or negative here, that wouldn't matter because I can see in your work here that you are treating this as having I can see in your work that you are accounting for all the signs correctly. But with the online homework system, that is one downside, that it grades rather rigidly, and you should just read the question carefully and kind of this is why you have more than one attempt and you don't get penalized between attempts. So that if you somehow miss the fact that they wanted you to indicate the direction as well with your answer, then you can get the once it says once it points out that this doesn't appear to be the correct sign. The question says, an iron nucleus undergoes an elastic collision with a stationary uranium nucleus. So for the purpose of setting up the questions, really, all the nuclear stuff, I don't really care. What matters is you have two masses that are colliding. So you have a target mass. Oops, why is that so thick? You have a target mass. Let me use capital M for that. And you have an incoming mass. Let me use lowercase m for, without the driver, it's a little bit awkward. You have lowercase m. And after the collision, it says, well, it undergoes an elastic collision. And it simply asks, what percent of the kinetic energy of the iron nucleus is transferred to the uranium nucleus? Assume the collision is head-on, one-dimensional. That does make it easier. It doesn't give you any more information than that. I think if you have some intuition of the type that you might have built up in one of the labs, you might have this intuition that if this was before the collision, then the picture you should have after the collision will look like where so looking at these mass numbers, iron nucleus is lighter, or it's less massive than the uranium nucleus. So this colliding object is smaller in mass. And you might have this intuition that in a collision like that, the smaller mass bounces back. If you have that intuition, great, that is correct. Now, what it is even if that were incorrect, there are also ways to kind of correct it after you work out all the math. So you might still assume a direction anyway. So, so kind of thinking through this collision, you might get this first. So you have some thing with the initial velocity coming in, striking, and then after the collision, the target mass goes off probably forward to the right. And if you have correct intuition, you realize the incoming mass will bounce backward to the left because M is lighter than big M. If you don't have that, great, it's fine. You can still move on without getting this part necessarily right. But this kind of diagram is useful for kind of getting a full sense of what's going on physically in this setup. And after you kind of work it through, then the thing is to go through the solution steps. And I think by this point, you are probably familiar with the conservation laws. So you would set up conservation of energy, conservation of momentum equations, and try to solve it. And my guess is a lot of people might get stuck at these steps. Like you wrote down a bunch of equations and then you can't quite solve it algebraically. You keep getting stuck when you try different things. So that's what the hint that I give is meant to address. And I think I tried to give as much hint as I could without giving away the answer. But in conversation with your study group leader, I realized, oh, maybe that's not enough, because it took me a little bit of time to work it back out. so that's why I want you to go over this question here so that I can kind of show you how carefully you have to work through these steps. And I guess the first few times you're going through questions like this, one most important thing probably is the willingness to go back in steps. Kind of realize you're in a dead end, scratch out whatever it is you're doing, and kind of try a different route that you haven't tried it before. So let me follow this advice here. It says start by setting up the conservation law equation. Yeah, I think I was going to do that. So let me do conservation of energy. It's an inelastic collision. That is the one thing that you are given. So which means the initial kinetic energy of the colliding mass, K naught, that can only go into kinetic energy of the two outgoing masses. So so kinetic energy 1 plus kinetic energy 2. All right, that's one conservation law. And because it's collision, you know there's a conservation of momentum involved, usually, probably. So let me write that down. So conservation of momentum. And in physics 4a, I like to write my equations in a way that every symbol I write down is a positive number. So that's why I'm going to write it this way. For conservation of momentum, I'm going to say the incoming momentum. I could have put a vector symbol, but it's 1D. I can just deal with the directions in science, and that's what I'm doing here. Is equal to, I'm going to say minus P1 to indicate momentum P1 going to the left in the negative direction. And it doesn't have to be written this way. I'm just writing it this way so that when I work out my P1, if I do, it's going to be a positive number. And at some point, I think at higher levels of math, engineering, and physics, you eventually kind of allow your variables to be negative. But at this point in your career, I think it's better for you to put the signs into your equation so that you are consciously thinking about the signs of your quantities. So yeah, so the initial momentum is equal to the minus P1 for the P1 that's going to left, plus P2 for the momentum of the big mass M, P2 that's going to the right. So those are my two conservation law equations. And this is basically full of unknowns. So I'm going to have to start substituting in other expressions. And that's where I have additional hint to follow. It says, for the masses of the particles, use that. That's something you can do if you are actually plugging in numbers. Here. And I think this is where I was trying to give a hint, and I think it ended up not being quite enough. So it says, one idea to possibly simplify algebra, express conservation laws in terms of incident and outgoing particles' kinetic energies rather than speed. And I think maybe some hint of that is here, in that the questions being asked, they are not in terms of velocities or speed, it's in terms of percent of kinetic energy. So if you have these quantities already expressed in terms of kinetic energy, it's probably going to be easier to work it out. So, and there's other reasons too, but with that as enough of a motivation, let me follow that advice here. And what I want you to illustrate is how to follow that advice. The last hint is, if you can't work out the algebra, then just to do it the easy way, the brute force way. But hopefully I won't have to resort to that. So the first equation here is already in terms of kinetic energies. So I don't think I need to do anything with that. So let me just label the equation 1. I have equation 2, which is in terms of momenta, and that's not very helpful. So this is where you have to remember the relationship between momentum and kinetic energy. You should remember that, well, kinetic energy, which you can express as 1/2 mv squared, and you have been, it can actually be expressed in terms of momentum as momentum squared over 2m. You can kind of prove this for yourself using momentum is equal to mv. So what I need to do is to solve this kind of mini equation for the momentum. And when you do, you get momentum is equal to square root of 2 times m times the kinetic energy. So that's what I'm going to use. And when you do square root like this, I think that's where it does benefit you when you write your equations this way. So otherwise, you have to go through other mental gymnastics or whatever to remember all the signs. If you're writing your equations from the start in a way where your variables are positives, then that kind of does take care of a lot of things. So let me write it this way here. The initial momentum can be written in terms of the initial kinetic energy. So that's going to be square root of, and the method incoming thing is the lowercase m, 2m times initial kinetic energy is equal to minus, remembering the minus sign there, times the square root of, mass is still the same, lowercase m mass, 2m. And for kinetic energy, I don't have k not 0, I have k1. So ke1. And then I need the last term here, plus momentum of big mass m. So it's a square root of 2 times the capital M times the kinetic energy 2. All right. Now, if you look at this carefully, you will see that you still have too many unknowns. You have, well, the incident kinetic energy is unknown. The outgoing kinetic energies are technically unknown. So you have 3 unknowns, 2 equations. That's not quite enough. There's a couple different ways you can handle that. One is to kind of, I guess maybe, let me put it this way. So the question, it never asks you for the energies directly. It's asking for percent of kinetic energy. So you can kind of think of expressing this in terms of ratios. So with the equation 1, I can do that by just dividing through by ke naught. When I do that, the left-hand side becomes 1. This is ke1 over ke naught, ke2 over ke naught. So this is one of my unknowns, x. This is other of my unknowns, let's say y. And you will see that that's a kind of a manipulation that you can do for both of my equations. In my second equation too, I can do similar division, divided by square root of k naught. When I do that, this k naught goes away, and I have under square root k1 divided by k naught, and second term under square root k2 divided by k naught. So you say, so let me just use those labels. I'll call this x, call this y, and basically my task is to solve for the unknowns x and y. And once you have x and or y, then you can see how that relates to this percent of kinetic energy transferred, and you can do it that way. So let me write down the cleaned up equations here. Equation 1 is equal to x plus y. And equation 2 is
square root of 2m is equal to minus the square root of 2m times square root of x plus square root of 2 big M times square root of y. So at this point, you have two equations, two unknowns. It should be solvable. And that's a good thing to know before you start, because these square roots are going to, it's going to make your life difficult. So yeah, you have to be prepared for that. And I'm not entirely sure if I remember all the solution steps. Went through this with your study group leader, and I still need to kind of think this through to remember. Let me do one more simplification, because I don't want to deal with extraneous symbols that I don't need to deal with. I say that if I divide this through by square root of 2m, lowercase m, that kind of simplifies two of the terms. It makes this 1, makes this minus 1, and it makes this one ratio of masses. It's going to be square root of big M over small m. So, it's just fewer things to write. I think it's going to be better. All right. So I have two equations, which are, just reminding myself, 1 is equal to x plus y. And the second one is now 1 is equal to minus the square root of x plus square root of big M over small m square root of y. And there are many different things you can do at this stage that'll kind of lead you into dead end. And when you've struggled long enough with the problems like this, you will eventually realize that what's giving you all this trouble are these square roots. So what if I didn't have those square roots? So let me just focus on that. I'm going to try to get rid of square roots first, and then I'll see what I can simplify, and I'll move on from there. So guess one thing I can try to get rid of square root is, what do I want to do? I don't remember all the steps. I may be trying this a couple different ways. Let me just try taking this and just squaring the whole thing. By the way, I'm not using substitution with this particularly, because this is what makes the algebra here complicated. Substitution may work, but I think sometimes, especially problems like this, ones that involve square roots or squares, that sometimes substitution kind of leads you down a path where it's not clear how you get out of it. So I'm squaring, I get expression 1 is equal to square root of this is plus square root squared, so just x. And then let me just do this term squared. That's going to be plus the ratio big M over small m times y. And then there are things that we call cross terms, which if you go through it, it's going to end up being minus 2 times the square root of big M over small m times square root of xy. I'm still left with the square root. That's a bit disappointing. Oh, but one thing I can do is I can so I see one way to kind of simplify, using this equation here and this equation here. I see a way to kind of simplify, because they share some of the terms. So if I do a linear combination, I will be canceling out some of the terms, and I'll deal with whatever expression remains. Let me label this equation 3. Oh, and I guess this is still 1. So what I'm doing is equation 3 minus 1. And when you do that, left-hand side becomes 0, equal to x's cancel out, at least that one does. And I have this big M over small m y minus y. So factoring out y, I'm going to get big M over m minus 1 times y minus 2 times the square root of big M over m square root of xy. I still have 2 unknowns. That's a bummer. Well, I think one thing that's good to try in situations like this is to try to isolate the square root. That's because I'm kind of on an autopilot here right now, and I'm thinking, all right, I have this complex expression. What do I do? Well, I know this is one of my unknowns, and I know one way. So one of the things that's complicating is this square root. And the standard way to get rid of square root is you isolate the square root term, which is this one, put it by itself, and then you square everything. That'll get rid of the square root. So let's do that and see where that gets us. So when you do that, so I'm going to solve it for the square root of xy. So let me just write it by itself, square root of xy for when I have solved for it. That's going to be equal to, so I guess I'm imagining I move this to the left-hand side, and then I'm multiplying through by 1/2 times square root of small m over big M. Yeah, that'll get rid of all the coefficients. And I still have this term here, which is big M over small m minus 1 times y. All right, squaring both sides, I get x times y is equal to 1/2 squared, so 1/4 square of those ratios, so small m over big M, and this thing in parentheses squared times y squared. Oh, one factor of y cancels. So I have this y canceling that y. So I have x, kind of a simple relationship between x and y. And this is a kind of a no-no when you are solving system of equations. It's, as a general rule, I try to avoid it. But here, I'm just going to be in a watchful fashion. I'm going to use this equation one more time. Normally, you want to avoid doing that because that's how you get dependent system of equations. But here, I'm just trying things out. And if I get dependent system of equation, what it'll end up giving me is like 1 equals 1. When I get that, I'll know I messed up. I have to go back and redo this. But I'm kind of crossing my fingers, hoping I don't get that. So let me see what I want to solve for. Kind of looking back. So the way x and y were defined, what percent of kinetic energy is transferred to the target particle. Oh, I think that's more directly related to y, because it's the kinetic energy of the target particle over the initial energy. So that gives you the percent that you're looking for. So so let me, so out of the equations 1 and 4, let me solve for y, eliminating x. So what that actually means is oh, this is already solved for x. So let me plug this into here and plug equation 4 into 1, and then try to solve it for y. So so plugging equation 4 into 1, I get 1 is equal to the x, which is this expression here, 1/4. Let me try to simplify this a little bit here. Can I? No, since complicated, let me not. Small m over big M over small m minus 1 squared times y. That is plus y. Okay, I can factor out y. So when I factor out y, it becomes 1/4. It might be worth kind of expanding this out. So let me expand it out. So small m over big M times expanding that thing out. It's m squared over n squared minus the cross term 2 times big M over small m plus the minus 1 squared 1. Plus 1 from the second term there, and I factored out y, so there's y factored out. Now I can kind of distribute that factor and see what happens. Distributing it, one factor of this squares get canceled, this ratio gets canceled, and I have a ratio of small n over big N at the very end there. So if you're doing this math in your head, you'll kind of see where I'm going with this. So let me just write it out so that you can see. 1/4 big M over small m minus, now I have 2 over 4, just minus 1/2 plus small m over big M plus 1. And, oops, oh, sorry, that's 1/4 there. So you say, oh, I have that 1 there. I can combine that with this. So it now becomes plus 1/2. So all this kind of complicated expression on the right-hand side, it does get simplified a little bit into 1/4 big M over small m plus 1/2 plus small m over big M times y. And I think you can actually simplify this a little bit more. You can kind of refactor this back in. But I guess that doesn't really simplify anything. So I can leave it here and just solve this for y. Say that y is equal to 1 over this ugly thing. 1/4 big M over M plus 1/2. I keep forgetting that 1/4. Plus 1/4 small m over big M. I guess factoring out 1/4 is one thing you can do. But let me just leave that there. So this is an expression for what we are looking for in terms of just the masses, which are given quantities. So you can plug in the numbers, see what you get. Let me actually do that. So one of the hints, by the way, was to, did I delete that hint? I might have deleted that hint. Oops. One of the hints, which I shouldn't have deleted, is it gives me the masses of the things. And it gives it in such a unit that the unified atomic mass, it cancels out, so I don't even have to plug that in, which is I wanted it. So let me just have that here, and then I can just plug in the numbers. Let me bring out my calculator here, clear everything. So I guess if I have just the ratio of the masses, I can just use that. So let me do the ratio of the small mass, 55.9345 to the large mass, 235.0439. Okay, that's that ratio. I'm gonna have that stored into memory. And here's the ratios in straight form. Here's the reciprocal of that ratio. So the way I should plug in it is, so 1 over parenthesis 4 times the ratio, memory recall, parenthesis closed, plus 1/2 or 0.5 plus the ratio, so memory recall again, divided by 4 is equal to the number in the denominator. So I take the, well, put that into memory and take the reciprocal 1 over what was in the memory. So 0.62. so that's the fraction. So in percent, it should be 62.11%. All right, let's plug in the numbers and see. I say this half jokingly, and this time it could actually be true. It could be wrong, and it would be embarrassing. 62.11%. All right, it was right. It wasn't as embarrassing. But I kind of want you to see how long and complicated this algebra was. And I think getting good at something like this only comes with the practice. And I can tell you how many times I've seen question like this and didn't know the exact right thing to do. Like even now, I'm only 80% sure as I'm going through the path that I have myself laid out. And questions like this, system of equations involving square roots and squares, is one where you might not make any mistake per se, but do things that will lead you down a dead end. And here, I've done this many times, and I had a sixth sense for avoiding dead ends. But even then, I had to break some rules. I used an equation twice, and if I wasn't careful, I could have easily had a dependent system of equations. So this is the question, it says derive the equations, giving the final speeds for two objects that collide elastically with the mass of object being this, speeds being this. Yeah. And I'm going to do this really quickly using a shortcut. And I'll leave it up to your judgment whether to use this shortcut or not. And really it comes down to, because there's another shortcut that I've seen people use that I don't know if there's a way for me to prevent that other shortcut. And the shortcut I'm showing you is at least the types of shortcut that even the professionals in the field would use. So, and I guess the other shortcut professionals might use as well, which is looking at the textbook. But sometimes the textbook doesn't have the exact equation you're looking for. So what do you do if, what do you do in that case? And the shortcut I'm showing you works more generally. So this is what the question is saying, derive the equations, giving the final speeds for, let me highlight the important part, two objects that collide elastically, which is telling us that kinetic energy is conserved. And really where it says collide is actually also telling you that total momentum conserved, because usually the things that we describe as collision momentum is conserved, especially if all the objects involved in the collision are involved in your system. If you have a wall or whatever, then okay, the momentum gets transferred to the wall, but here momentum is conserved. And then it's saying with the mass of objects being m1 and m2, okay, those are the symbols they are telling us to use. So if you note these conservation laws that apply in this setup, from this single phrase, collide elastically, then you know what equations to use to derive these expressions. You are using conservation law strategy. We've identified two conserved quantities. So let's write down two equations based on those two things. And I think they are missing some information. And let's just say they are colliding elastically. And this is a head-on collision. If it's not a head-on collision, then you would have to consider different angles that things can go on. And that's really why I'm assuming it's a head-on collision, because otherwise I need the data and it didn't tell me what angles I can use. So with the head-on collision, treating this like a one-dimensional situation, my first equation is conservation of kinetic energy. So the total kinetic energy initially is going to be equal to total kinetic energy finally, and I'll parse out exactly what this is. And my second equation is conservation of momentum. The total momentum initially is going to equal total momentum finally. So total kinetic energy initially. So I have objects M1 and M2. Let's just start writing them out.
I have kinetic energy of m1. That's going to be 1/2 m1, and its speed v1 initial v0 squared plus the total initial kinetic energy of m2. It said it's at rest, so it's going to be 0. That's equal to the final kinetic energy. So I'm going to use these symbols, V1 and V2, for final speeds, which is what they're telling us to use, I think. Um, 1/2 m1 V1 squared plus the final kinetic energy of V2. It probably gained some kinetic energy through the collision. 1/2 m2 V2 squared. So that's my equation 1. For my equation 2, I'm going to give a statement of conservation of momentum. So initial momentum, it's m1 times v naught plus the zero momentum for v2, which wasn't moving, is equal to, and here one could think through what kind of collision it might be. As you think about M1 and M2 colliding, I think it's easy to think of M1 being bounced back and maybe write down minus M1 V1. Let me show you a slightly different approach, which I would like to call is a more formal approach. Because actually there are situations where M1 will continue to roll forward. So what I'm going to write down is I'm going to simply write down M1 V1 plus M2 V2. And what I will insist on here is I didn't make any sign error. What I've written these symbols for is I've written them as a vector quantities. So if, defining this as my positive x direction, if my v1 and v2 turn out to be positive, then that's the solution telling me that these are moving in the positive direction. Somehow if one or both of these quantities end up being negative, it's the solution tells me, oh, one of them is bouncing backward. So I'm just gonna just not include the signs into my equation. And you will see me start to do that with some of the more formalistic equations. Conservation law equations are first of those equations where you will see me doing that. So I have this, and normally the next 15, 20 minutes will be spent going through algebra to solve this all out. Instead of that, I'm going to use the amazing shortcut of computer algebra system. I'm just going to type in these equations and let the computer algebra system do the solution. Let me make sure all my variables are declared. Okay. And my equation 1 will be the conservation of energy is equal to 1/2 times m1 times v1 squared plus 1/2 times m2 times v2 squared. Okay, and equation 2 will be conservation of momentum m1 times v0 is equal to m1 times v1 plus m2 times v2. Okay, let's make sure I typed those in correctly. And I'm going to have a solve function, solve for a system of equation. That's the system of equation 1 and 2. And I'm going to heavy solve for v1 and v2. Me telling the system that also tells it that the other variables may be treated as known quantities. So, oh, that was quick. Oh, it's solved. So it gives me two solutions, which actually makes sense because I have that squared quantity there. So there should be two set of solutions. And the first solution, if you read through it and think through it carefully, hopefully gives you this sense that, oh, that's the solution you get when these two balls have simply missed each other. The M1 retained its initial speed, and M2 continues to not move. So really the solution I want is the second solution. So let me say my solutions are really the previous output, second element. So this is the solution I'm working with. And oh, I don't have to plug in any numbers because it's asking me for symbolic answer. I'm just gonna symbolically type in this. So V1 is gonna be M1 minus, I need the subscript, minus M2 times V naught divided by m1 plus m2. And I think even though this looks a little ugly, it'll be fine. It won't. It'll recognize the correct expression. 2 times m1 times v naught divided by m1 plus m2. Interesting. All right, let's see if they are correct answers. Yep, they are correct. Good. And again, if I'm doing this by hand, it would have taken me another 10, 15 minutes, or maybe 20, I don't know. So it says, consider your answers carefully and match the conditions below with what you physically observe. M1 equal to M2. Then you see the V1 goes to 0. So you have object 1 goes to complete stop. Yeah, that's C. If M1 is greater than M2, interesting. So this is positive. Nothing interesting here. Okay, so object 1 will continue to roll in the positive direction. That's what I was saying. It could be positive. So continuous, yeah, that's A. And the last one, M1. So this quantity will now be negative. So V1 as a vector quantity is negative, which means the ball M1 is now rolling in the negative. So it bounces backward after collision. That's D. So yeah, I'm using the shortcut that I'm a little bit um, two-minded. I'm ambivalent about this particular situation. People using computer algebra system, which is because I do think the algebra exercise you get here is good exercise to have. You'll see me do that in lecture, so do that for your own learning. At the same time, if you want to use computer algebra system, take the exact shortcut I've taken now. I think that's totally fine. I don't think other than missing out on a little bit of algebra practice, I don't think you've missed out on anything great and big. So that's my demo of approach that I feel a little bit ambivalent about. But I feel better about this approach than simply looking up equations from the textbook, which it's not cheating, but you learn less from doing that than from doing this. Here, you at least learn how to use the computer algebra system. So. I think about a year ago, I learned a new way. Well, I guess it's not actually new, but it was new to me. I learned it from ChatGPT. So it's a quicker way to do elastic collisions. Now, conceptually, it is. I do think it is more complicated than just a simple application of conservation of momentum and energy. That's conceptually a lot easier. This particular formula that can be derived for one-dimensional elastic collision, it makes math a lot easier. So let me present this second version of all the elastic collision questions you have in the homework so far. And you have seen me approach this with all the complicated algebra. Let me see if I can group them all and just do them all together. And because the algebra is going to be so much easier with this particular approach. So I'm going to go to the lecture where I go over all this. It's in lecture 14. What's called the relative velocity relationship. If you're on a Google search, that's how you would find it. And I'm just gonna basically look up the formula here. In this lecture, I go through the whole derivation of that. Don't need that. You can watch it. You can go watch it if you want to see the derivation. At the moment, all I'm interested in is this. The relative velocity formula as derived. The primed quantity there means it's the after collision picture. I'll use the labels of the initial and final. So relative velocity relationship. And I want to make it clear that people don't abuse, misuse, use it in context where it doesn't apply. So let me clearly say it's for elastic 1D collision only. And what's derived here is, let me write it down. So you are looking at two objects colliding. One of them is object 1 and the other is object 2. And it's a general relationship. One doesn't have to be at rest or anything. V1, and their masses can be different too, even though this formula doesn't have any masses in it. V1 initial plus V1 final is equal to V2 initial plus V2 final. And as you will see, when you see the derivation that's done in this video, this this relationship already contains the information that it's elastic. So when you use this equation, it's kind of physically equivalent to use conservation of kinetic energy. The advantage of using this formula rather than conservation of kinetic energy, which, let me just write out. The conservation of kinetic energy says 1/2 m1 v1 squared, initial, plus 1/2 m2 v2 initial squared is equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. This is what conservation of kinetic energy says. The advantage of this expression over this is that this is linear equation. It doesn't involve any squares, so that makes your algebra just so much easier. It's a linear equation, and I kind of talk about in this video what the trade-off, catch of using this formula is. But other than that catch that you will see mentioned in this video, it's equivalent to using conservation of kinetic energy equation. So for the purpose of this problem solving, I'm not going to use conservation of kinetic energy. That's the whole point. You already have my other videos where I do use conservation of kinetic energy to do these elastic collision questions. So using this relative velocity relationship, let me approach these elastic collision questions. Now, I do need a second equation to solve for two unknowns that's going to come up eventually. And the second equation that I'll continue to use is conservation of momentum. All these collisions that you will see conserves momentum. So I will say mass 1 times the initial velocity of 1 plus mass 2 initial velocity of 2 is equal to mass 1, the final velocity of 1, plus mass 2 times final velocity of 2. And I'm going to treat these quantities like they are vectors. They can be positive, they can be negative, and the signs will indicate whether it's moving in the positive direction or negative direction. So these two will be the equations I will use for every one of the problems that you will see me do now. So this is the other question. Now the question itself asks about kinetic energies, but this is what I have to say. Once you know the velocities or post-collision velocities of these particles, then kinetic energy is easy to calculate. So that's what I'm going to do first, using these two equations that apply to elastic 1D collisions, particularly the relative velocity relationship that encodes the kinetic energy conservation into a really simplified form. I'm going to find their final velocities first. And once I find their final velocities, then I can figure out, okay, what percentage of kinetic energy is that? So, let me say an alpha particle undergoes an elastic collision with a stationary cold nucleus. Do they give the... Okay, we have the masses of particles, good. Yeah, so let me just copy down those masses, and then I don't have to keep them up. So mass of the helium particle is 4.0026. I think this is a unified atomic mass unit. It's some uniform reference number. That's, I think, all we care about. And the mass of the gold particle is 196.9666 U. I probably could have used their mass numbers 4 and 197, and it would have been close. But let's just be precise. So the very first thing to do is for this picture where I have a gold initially at rest. So let me say this is V2 initial, that's 0. There's gonna be a helium that comes in with some velocity, V1 initial, and then they will collide, and after collision, I think the helium will bounce back with V1 final, and I'll keep it as a kind of signed quantity. So my V1 final will end up being negative. And I'll have gold that's gonna be bouncing forward with the V2 final that's no longer 0. So it asks what percent of the kinetic energy of alpha particle is transferred to the gold nucleus. So ultimately the answer that they are looking for here, it's the ratio of the kinetic energy of the gold after collision over kinetic energy of helium before collision. Or in terms of all the quantities, it's 1/2 mass of gold that I have times V final 2 squared divided by 1/2 mass of the helium times V initial 1 squared. Now I don't technically have a V initial 1, so what I would do is I'm going to get an expression for V2 final in terms of V1 initial, and then I should have enough information to do this calculation with the things that cancel out and all that. So our first goal right now is to solve for V2 final, and that counter intuitively means I'm actually going to solve for V2 initial first, because I'm going to eliminate it from my system of two beautiful linear equations. So let me solve for V2 initial from my V2 initial. What I'm solving for is V1 final. Yeah. So let me solve for my V1 final. That's the currently unknown, presumably, speed of the helium particle after the collision. So solving for that, out of equation 1, I have V1 final is equal to V2 initial plus V2 final minus V1 initial. Simple. Plug that into the conservation of momentum equation. Then I get M1, let me write it out as mass of the helium particle times, I'll keep V1 initial as it is, plus M2, that's going to be mass of the gold particle. Oh, but V2 initial is 0. V2 initial, which will be 0. So this simplifies my expression somewhat. And I have mass of the helium times, now I use this expression instead of V1 final. So it's a V2 initial, which is 0, plus a V2 final, which I'm trying to solve for, minus a V1 initial, which hopefully I can express everything in terms of. Plus, I have mass of the gold times the V2 final. Yeah, so I'm still trying to solve for that. So I see that on the right hand side is where I have this V2 final that I'm trying to solve for. So let me combine the like terms that way. So on the right hand side, it looks like what I'll have is I have this term and this term. I can imagine collecting the like terms, factoring out V2 final. So it'll be mass of helium plus mass of gold times V2 final. Let's take those terms taken care of. One of the terms was 0, so I really have this term that I have to just move to left. So let me write down the left hand side with this term, move to the left. I have mass of the helium times V1 initial, now plus, that's interesting, plus mass of helium times V1 initial. So these are the two exact same terms. So get rid of one, make one of them 2. So it says, let me just move this to make myself a little bit of room. Let me solve for V2 final here, and I think I can wrap up. So V2 final, so dividing both sides by basically the sum of the masses, is 2 mass of the helium times V1 initial divided by the sum of the masses of the helium and the gold. Oh, so I think let me do that substitution here. The writing's gonna be a little bit in the way, but yeah, I'll just do it, suffer through. So saying equals 1/2 canceled out. I have ratio of the masses of gold over helium, and let me square them as I go. So I have 2 squared, 4 times the mass of the helium squared, times the V1 initial squared. It's gonna get cancelled out, but I'll put it in anyway. And then I've divided by those masses squared. Let me just put it on the denominator, just to, I don't know, save room. Sum of the masses squared times, now what's actually on the denominator, I already took care of the mass of the helium. I have a V1 initial squared. So the V1 initial, which we were assuming we knew, we are hoping it would cancel out, it does cancel out. So my final answer is this ratio of masses. So let me plug in this ratio of masses into Wolfram alpha, and let's hope the answer is graded as correct. So I'm going to be putting masses in this way. I'm just going to put in the numerical value of this coefficient, and the unit, U, the atomic mass unit, will just cancel out. I'm just going to trust that will happen. So mass of gold, 196.9636, divided by mass of helium, 4.026. Okay, that's the coefficient up front. I could have done a little bit of simplification with the cancellation, but I only get to cancel one factor of mass of helium, so it didn't seem like a lot of benefit. So 4 times mass of helium, 4.0026 squared, because I chose not to cancel it, divided by the sum of the masses, 196.966 plus 4.0026, and then this thing squared. So that should give me the right answer. Now it seems a little bit large. That makes me worry. Maybe it's right. So the answer they're looking for is percent. This is just the ratio. So for the percent answer, I need to multiply this with 100. So it's a 7.81%. Seems large to me, but maybe it's not. Oh, all right. I guess that's right. I might me remembering saying smaller number might be, I don't know, proton hitting gold, maybe. But yeah. This again, I think it took me like 10 minutes. That's a lot quicker than what using the kinetic energy formulas would have been. So yeah, it's again it's the advantage of the relative velocity relationship that that math is so much easier. You only have to deal with the linear equations. Now the downside of it is, I guess I would have presented as twofold. One, I think conceptually it's a little bit more opaque. Like it's not as clear like what is being conserved. You have to remember for yourself that when you are using this relative velocity relationship, it only holds for elastic collisions in 1D. So that's the situation that you are allowed to use it in. So conceptually it's more opaque, and the other downside is because it's conceptually more opaque, you might make a mistake remembering this formula. I wrote this down in the form that I will remember. I think writing down in this form, I won't ever make a sign errors in remembering this. But most textbooks write it in a different way, and I think the form in which most other textbooks that have this formula, not ours, Giancoli has it, Young and Friedman has it. The way those other textbooks presented, I think it's really easy to make a sign error. So those are the two downsides. But like if you are careful with it, it's like sharp knife. It can be a great tool.